nice one. This is a nice, I like this. I like this much better than the hypergeometric. This is, if you can like distributions one more than the other. Poisson distribution, as it's called, is something we use for systems where we count something. I think we had it could be the number of calls to my call center within the next hour. It could be the number of customers to my shop within this day. It could be the number of jobs submitted to this server that I'm in charge of administering. It could be the number of clicks on my online website within a day. So we count something within time. That's the typical situation where the Poisson distribution is a relevant distribution. It could also be counting something in space. It could, of course, also be the space we're all of us talking about that now, but when I say space, I more mean for instance, in a petri dish, if you count bacterial colonies in a petri dish. If you count eels in the seas of the world, if you count fish, there's a nice story about the eels on the website. Go and have a look. One colleague of mine saved Öresundskonsortiet, I think 300 or 400 mil Swedish kroner in a court thing going on in the Swedish Environmental Court of Law, because they thought they could accuse Öresundskonsortiet for being the reason for why the eels have disappeared in Öresund after the bridge, which is, of course, very unfortunate for all of us. But the thing is, if you look at the numbers and if you model them and analyze them by Poisson-based stuff, which they are, then you will realize that the eels have disappeared from Öresund, most likely not due to the bridge, because they disappeared all around. So it's no wonder we don't have any eels, because they don't come anymore, because there are no eels around for many reasons. So, Poisson is nice. When we talk about the Poisson distribution, that is a model, a distribution for a phenomenon where we count something during a time period or within an area. We have to know one thing to be able to work with it, to know the probabilities, and that is what we call the intensity. It's called the lambda, which is the number of events by time, per time unit. That's the lambda. Having the lambda, the density function is a nicely looking function like this. It's the density. So if let's say if we wanted the probability of exactly 2 events, 2 eels within an area at a certain time, then we take the intensity to the power of 2, we take the exponential function to minus the intensity, and we take the number factorial, x factorial, like we discussed before. This actually defines nicely a density function if you add up all of these numbers, all of them, because note that there is no upper limit to what potential number could come out here. If you throw a coin 10 times, you don't see more than 10 successes, right? By the system has an upper limit of 10. When you count numbers in the nature somehow, there is no upper limit in a way. And actually, this is a bit of a mathematical analysis. We're not going to prove how this pops up, but it's, if you like Stirling's formula and other things like that, it's of course related to some standard mathematical analysis like that. But here for us it's just a probability distribution called the Poisson distribution. And this is the density function. Let's try it. Let's try it. Assume we have an intensity of 0.3 patients per day of a particular type coming in to our hospitals, in this case, coming in due to air pollution, just to take an example. What would then the probability be that at most 2 patients are put in hospital in the Copenhagen area due to this thing? Well, let's Let's see what we have. What's the variable, random variable we're talking about? This is something we should always think about. I would say we're talking about the number of patients on a day. So we're counting something within a day. So we should make sure we are on top of that. It follows a Poisson distribution. What is the probability? In this case, this is the probability. This is, of course, the first challenge when we are given exercises like this, is to put these words into formula. And of course, this can sometimes be what, at least, at most, highest, long. What exactly is he talking about, right? We have to think there. Probability at most 2 patients, at most 2. That must be less than or equal to 2, right? 0, 1, or 2. So we have to maybe sort of say it a few times in your head to make sure, yeah, that's the probability we're being asked about here. Good. Then I can continue. Then I put the nature of the problem, I put it into math, and then I can use my math to come up with the answer, right? That's the thing. I would need to use this lambda 0.03 intensity. Having done that, let's see. I didn't bring, I thought I had the numbers, but let's go to R and look at the numbers. By the way, I skipped from before. I mean, the hypergeometric is also in R, but let's not dwell on that now. I like the Poisson much better. Here it is. What is the probability that at most 2 patients are hospitalized? That was the question I was being thrown in my face just a second ago. So I had a p binom. I have a p-Poisson function giving me the probability of being less than or 2 with this lambda equal to, and that probability is not surprising when you think about it. When the intensity is only roughly a third of a patient, that is a patient for each more than 3 days, the probability of getting 0, 1, or 2 patients on a day, that's what most often happens. So it happens quite rarely, only less than 1% of the time that we get more than 2 patients on a single day, right? That's the other way to put some interpretation. What about the probability that we get exactly 2 patients? Well, we have the d-Poisson for density. Density probability, right? Density accumulated probability. Well, the two event also is quite a rare thing. Only 3 out of 100 days we get 2 patients. What about, now we were not asked, but let's look at the other 2 events that added up to the one from before. What about 1 patient? Every 5th day we get 1 patient. What about no patients? We can stay home. Well, 74% of days we don't see a patient. That's how it is. Let's see. A couple of more questions is coming to us on the slide, but let's do them here. What is the probability that at least one patient, that is 1, 2, 3, 4, 5, 6, 7, up to 1 million. Let's say there are many D, we should compute this D probability many times, or we go the opposite way. We take 1 minus less than or equal to 0, meaning that we get from, I don't think I agree on this one actually. Wouldn't you say that at least 1, I should only subtract the 0? Doesn't that make more sense? At least 1 would say 1, 2, 3, 4, 5, right? So I should only subtract the 0 actually. That would be 26%. Let's go back to, there is one little point in this. This is what I did. You can play around with that. Yeah, here's the point I want to make as the last thing of the Poisson. Because maybe we cannot just stick to working with single-day events. Maybe someone asks us about, like here, I'm just interested in what is the probability that we get exactly one patient during 3 days? That's my question to you, not during 1 day. What I started out with was a 1-day intensity of 0.3. And then I tell you we can use common sense. What would you guess that the 3-day intensity is when the 1-day intensity is 0.3? It's not a trick question, common sense rules. 0.9, of course. So it's just to make this point, it's valid to do these common sense changes from the different timescales that we face. That is perfectly valid. So we could take the Poisson distribution, not with 0.3, but with 0.9 days, and work with that one instead, and then count events over 3 days instead of 1 day. That's perfectly valid. Having done that, we can get the result from I was asked, and the number itself is not so important now, so let's not do it. That was the Poisson distribution.